good morning to one and all present here. I, Mrs. Neha, Assistant Professor, Department of CSE, welcome you all for the International Conference on Harnessing AI, Quantum Computing and Autonomous Systems for Sustainable Future. Today we gather here to celebrate knowledge, collaboration and the spirit of inquiry that drives our academic and professional journeys. I request all the dignitaries to light the lamp. May the divine power bless us all.
Song. Divya ma'am. Divya ji ma'am. Song. और कुटी दिवी सर.
नमस्ते सुमकामाये श्रीपीठे सुरपूजिते
I would like to remember in this present occasion our beloved founder and chairman, Dr. S.M. Venkatpati ji, East Point Group of Institution. I would like to welcome our respectable chairperson, B.L. Ramadevi Venkatpati ma'am, EPGI, in her absentia. Welcome ma'am. My hearty welcome to our CEOs, Shri Pramod Gowda sir and Shri Rajiv Gowda sir, EPGI, in their absentia. Welcome you sir. On this momentous occasion, it is our proud privilege and fortune to welcome Mr. Balaji Rajakesari sir, Scientist, Control System Group, Controls and Digital Area, UR Rao Satellite Center, ISRO, Bengaluru. Welcome you sir. I request our principal, Dr. Pradeep Kumar Dikshit sir, to welcome our guest by presenting a bouquet. Thank you, sir. A leader's greatness lies not in power, but in the ability to uplift others, a virtue we truly admire in our beloved principal, Dr. Pradeep Kumar Dikshit, sir. I extend a warm welcome to you, sir. I request our Vice Principal, Dr. Yogesh, sir, to welcome principal by presenting a bouquet. Thank you, sir. Leadership is the art of turning vision into action, a quality shown by our Vice Principal, Dr. Yogesh, sir. whose steady guidance transforms goals into achievements. I request Dr. Manimoli ma'am to welcome sir by presenting a bouquet. When vision meets dedication, transformation begins. A legacy beautifully upheld by our HOD, Dr. Manimoli ma'am. I request Bhagyalakshmi ma'am to welcome our HOD by presenting a bouquet. Thank you, ma'am. I welcome Dr. Anand sir, HOD of AIDS and our esteemed General Organizing Chair, whose leadership adds great value to this event. I request Dr. Hina ma'am to welcome sir by presenting a bouquet. Thank you, ma'am. I also welcome all the heads of the department, faculty members, and participants. Welcome all of you. It's my proud privilege to request our visionary leader, our principal, Dr. Pradeep Kumar sir, to take the stage and inspire us with a few words.
Good morning. So, at the outset, I congratulate Department of AIDS, CSC, and ECE for taking the pain in organizing this international conference. Maybe it is done in very hurry, right? So, I request all the departments and the participants, research scholars, faculty to take this opportunity and build your network. The purpose of the conference is to build a network. And don't leave the people if they are presenting paper. Right? Don't take too much time for the questions. Ask one or two questions, and during the tea break and lunch break, you can drill them. Right? So I once again congratulate. I don't want to take much time. It is all formal things, inauguration. More time has to be spent for the technical sessions. Right? Thank you very much.
I request our Honorable Vice Principal, Dr. Yogesh sir, to accord a formal welcome to the dignitaries.
A very good morning, respected dignities on the dais, Honorable Principal Sir, Honorable Chief Guest Balaji Sir, Ashok Sir, Manimoji Madam, and Anand Sir, respected head of the departments, respected faculty members, and today's chief guest. In fact, all the research scholars are the papers who are going to, the researchers who are going to publish the paper, present the paper here. It's a great occasion to be part of this particular inaugural function. As we know that in the present AI and quantum world, huge amount of investment has been done in these two specific verticals. If you specifically want to talk about quantum computing, which is the key word in today's international conference, as per stats, Government of India has launched a unique program. They have invested around 8,000 crore in the name of National Quantum Mission. By the year 2023 to 2031, to place the India among the top 6 quantum research countries. So that's the goal of the Indian government. In fact, top-notch institutes of our respectful Indians research think, CDAC, IAC, TIFR and IITs are leading this particular program. with reference to India. When it comes to international level, US and China are also investing around $10 billion each in their national quantum computing programs. So this clearly reflects how much amount of investment and the work has been carried out in the quantum computing. So keeping this thing in mind, we initially myself, Manimoji madam and Anand sir thought that why don't we have a program or an international conference on this particular area. I think we have got a very good response. I sincerely thank all the research papers who have come across throughout India. We sincerely thank you, and I also wish all the best for the research scholars who are going to present the paper. Thank you, everyone.
Thank you, sir. Now I request Dr. Anand sir to speak a few words.
Respected guests, my dear colleagues, as well as my dear students, I am welcoming everyone present here on the dais as well as off dais. So it is my privilege to welcome everyone for the inaugural function. Thank you for attending this function. So we are gathered here to drive the innovation as well as to share the ideas as well as shaping the innovations for tomorrow's future. That is our great commitment. We are there here to do this sort of the works for further. So once again, I am wishing everyone for attending this conference. Thank you.
I request our organizing chair, Dr. Hina ma'am, to say a few words to mark this special event.
Good morning, one and all. Respected chief guests, esteemed keynote speakers, distinguished researchers, faculties, colleagues, delegates, and students. It is with immense pride and academic enthusiasm that I welcome you to the International Conference Harnessing AI Quantum Computing and Autonomous System for a Sustainable Future. This conference is designed to be a collaborative forum for the presentation and discussion of current research trends and future direction in transformative technologies that are reshaping scientific, industrial, and socio-economic landscapes. Artificial intelligence, quantum computing, and autonomous system are no longer siloed disciplines. They intersect in complex, high-impact ways, pursuing everything from intelligent decision-making systems and cryptographically secure communication protocol to self-optimizing machines and sustainable urban infrastructures. We are pleased to share this year conference attracted 76 high-quality submissions from researchers across multiple disciplines. After rigorous review process, 59 papers were accepted for presentation and 11 have already been selected for publication for Scopus Index Journal. This affirms the scholarly merit and application potential of the work being shared. The technical session over the next 2 days will feature diverse range of contribution from deep learning architecture and quantum gate implementation to autonomous robotic edge AI framework and real-time optimization system for sustainability. I take this opportunity to express gratitude to our keynote speaker, session chairs, reviewers, organizer, committee members, and supporting staff for their dedication and unwavering commitment in making this event success. Let this conference serve not only as a platform for presenting research, but also a catalyst for interdisciplinary innovation and global collaboration. Thank you and wish you all a technically enriched conference experience. Thank you.
Thank you, ma'am. I now request all the dignitaries to release our conference proceedings. is with great honor that we introduce today's keynote speaker, a distinguished scientist and visionary leader in the realm of space technology, Mr. Balaji Rajakesari N. Currently serving as scientist cum engineer at the Control System Group, UR Rao Satellite Center, ISRO, Bengaluru. Mr. Balaji brings a wealth of experience spanning prestigious national missions and cutting-edge research. His academic journey is equally remarkable, holding a BE in computer science, a gold medalist in MTech and MBA in systems, and currently pursuing a PhD in expert and autonomous computing for system-borne systems. With prior industry experience at Wipro and a stellar trajectory at ISRO, Mr. Balaji has contributed a high-impact projects such as IRS, INSAT, IRNSS, and interplanetary initiatives. He has held key leadership role as Deputy Project Director for missions including IMJS, GSAT-32, GSAT-7B, Venus Orbiter, and served as Project Manager for GSAT-20, GSAT-30, and GSAT-31 and more. His remarkable work spans AI-based evolution on onboard software, software fault tolerance in spaceborne systems, machine learning applications in spacecraft health diagnostics, and control algorithm development for autonomous station keeping. Mr. Balaji is also a sought-after technical speaker, having delivered keynote addresses at esteemed institutions including VIT, Christ University, Bangalore University, and others across the country. I now invite our keynote speaker, Balaji Rajakesari sir, to take over and enrich us with his valuable insights.
I was reading 2008 6 months training. I started first 3 months actually. Only actually that training groups will be that's one madam. Very nice mission. Whenever you record, connect. Balaji was Karnataka Balaji. He's a veteran who retired. Balaji. He is the first candidate who completed PhD. I joined before that. 2008 I selected. And that's again issue was that. So 1 year delay. By the time I started working, after that, I joined. immense training that was yeah, very much. Yes, yes. Only interview.
Hey, seriously.
Dignitaries, principal, vice principal, department heads, professors, assistant professors, and below students. Very good morning to everyone. Very good morning to everyone. Okay. Did you know anybody knows about what is a spacecraft or what is a satellite? Yeah, anonymous answer also well and fine. You can give. I'll give my introduction. Before that, I want you to know that what is a spacecraft. Every time in the news you will hear that a satellite is going launched by ISRO in Sriharikota. So and so. What it actually means, what is, as a layman, you think about spacecraft or a satellite? Anyone? This interactive session only, not it will not bore you. Just I want to give some insights about the spacecraft, what our Indian research is doing in the space industry.
About 10 kilometers flying.
About 10 kilometers flying object. This is a spacecraft. Correct? Okay. Any other, not into more into technical about the spacecraft. Just to give you think that I'm a layman. I don't know anything about the spacecraft. How I can interrelate spacecraft to my idea. How I can narrate it. In space means everything is imaginable, right? We couldn't think that this is a stool, I can touch and feel it. This is an object, so I can speak about it. But what about that imaginary thing? What space? Space is it's a zero gravity area. How the spacecraft interacts, all those things. If I want to think as a layman, how I can narrate? Okay, simple way I tell you, spacecraft. Okay, you think that spacecraft is a self-oriented hostel student who came far away from the home. Okay, home is equivalent to Earth, and came in the very strict environment, untethered environment like this college or any institute. That is called space. Correct? With no current, no Swiggy order, no mother especially, then how you will manage? So you have to come with your some of the things to survive. What are the survival skills? First I need power. Correct? So power means student has to bring his own battery charger or power bank. Correct? Next is structure. Structure is required. Structure is a big suitcase. It is well organized of your things. That is the structure. Next, coming to thermal control. You are feeling very hot. So your room has to be occupied with AC. So AC you can switch on to control, cool yourself. Or if you are very cool, you have to bring your own sweaters to manage. So thermal management is required. Correct? Over to that, onboard computer is required. Means your hostel roommate, or if you are self-sufficient, you are more brainer than everyone, you can manage yourself. Otherwise, one of your roommate should be well enough to train you in all the guides and aspects. So OBC, onboard computer with some software inside it. So that is required. Next, coming to control systems, AOCS. How you will manage AOCS? How you can relate that AOCS? If you are, if you should not fall away from the treadmill. If you are a gym-oriented guy, you are keep on trolling in your treadmill, it should not fall. So you need a balance. So control system is required. Correct. Finally, payload. Spacecraft has required some payload to take images. Payload is your final year project. So combinedly, if you think like that way, so your spacecraft also doing it the same way. It also required a structure. That is a structure which is evolving around the globe. It needs a thermal management. We don't know the untouched environment, how it will be, how it will project. So you have to sustain your stable platform there. So you should not hit extreme temperature. You should not go extreme temperature in a cold way as well as also. All this comes under thermal management and main onboard computer. So spacecraft has to think what to do, how it has to interact with the Earth. Correct. Mainly telecom and telemetry. If you are in a hostel, you have to call your mom saying that how are you? You have to interact with them, correct? All these things and all is required in spacecraft also. It has to interact with the Earth to saying that I am okay. What kind of things you want me to do? What kind of images I have taken, I have to give you. All those things, interrelated things to be done, correct? So spacecraft, apart from this kind of analogy, spacecraft is vehicle designed to fly in and operate it in a outer space. There is a zero gravity area. That is untethered environment. We cannot think it how it will. So as per our research, how it could be extreme temperature in the case or how to behave, everything should be predetermined. Okay, this is the spacecraft. Anyhow, I am Balaji Rajakesari, who is working as an onboard software designer for IRS, INSAT, Interplanetary and Indian Nano Satellite missions. And I am the software developer who has to write the code that is flying 37,000 kilometers apart from the Earth's surface. There you should not redo. There you should not control or delete. There is no retry option like what you are doing in your lab. Correct. So we have to develop a stringent software that should infinitely work in the space until the satellite lifetime gets ended. Correct. I am welcoming you, circuit branch students, who is speaking ECE and CSE and its derived associated branches, who always think that there is a debate, right? ECE and CSE. ECE will always tell that electronics is a king. CSE will tell us software is a boss. Correct? That will be there. So I am welcoming you. I am taking you some insights about the ISRO space program. Welcoming you one and all. Thank you. As I said, the national interest, you never thought that news will come that spacecraft has launched by this day. With us coming 30th also NASA satellite and ISRO combined satellite is going to launch. NASA ISRO synthetic aperture radar, which is going to launch by this 30th. Okay, I am also part of that team, and what I am trying to convey here is we don't know what kind of satellites we are developing and throwing to the nation. As per the nation interest, we have vast varieties of interests. First, prime and foremost thing is disaster management control, weather forecasting, and agriculture oriented. These things we have to capture, like IRS. That is called Indian remote sensing satellites. So that will come under Earth observation satellites. So these are some of the space applications, vast things. Earth observation satellites is a satellite which is placed in a 600 kilometer of orbit. That is polar orbit. Geosynchronous, not geosynchronous, it's a polar sun synchronous orbit. Okay, which is every 1 hour it rotates its orbit. Why this kind of spacecraft is required? Assume that you have cultivated paddy in your East Point area. There is a vast area, you cultivated paddy. So paddy has its own growing stages, from seed to it having different stages. Flowering stage, and then milking stage, then post-milking stage, final eradicated stage. Correct? These kind of stages, I want to monitor each and every day how the plant is grown and what is the color and texture it is get transformed from initial to the final stage. So I know that spacecraft is coming over my Bangalore region. What time? Correct? So assume that this is the Bangalore region. Spacecraft is coming around every day 6 o'clock. 6 o'clock in the morning. So every 6 o'clock when it crosses the East Point College or Bangalore region, it has to turn the spacecraft that is pointing that camera towards your East Point and click a snap. Daily the snaps will be taken continuously over the 120 days of time, or what is the yield time of the paddy. So with this what you will get, researchers will, that high resolution cameras will be protected. Even pinpointed area also will be clearly notified in the camera images. So what it will give, how the paddy is cultivated, what is the grown and stages, and what are the things they have put to cultivate the paddy. So when coming to the sterilization, everything will be accounted, and main thing texture and the grow level, everything will be known to the data is required to analyze how the paddy will comes and what are the inputs we have taken and what are the feeds we have given to the paddy to cultivate to grow. All these things will be notified. So these kind of satellites are coming under space earth observation satellites, like Indian remote sensing satellites, mainly for agriculture and disaster management and animal husbandry and forest disaster management. All those things we can easily monitor. Actually, this is like with the DSLR cameras, you are taking continuously, you are taking photos. Whether it is useful or not useful, we are giving the data to the society to analyze it. Okay. So these kind of things are called surveyors. Mainly surveyors is called earth observation satellites. Coming to the navigation satellites. What is a navigation satellite? A satellite which is launched, which is put into the orbit in geostationary or geosynchronous, which is 36,000 km apart from the Earth. So Earth rotation as well as spacecraft rotation will be approximately same 24 hours, which means every time spacecraft and the Earth and the spacecraft will be in touch. It will never lose the control because both are having a same rotational speed. So 36,000 km apart you are putting the spacecraft, whereas IRS is 600 km above the Earth. This is our surveyors. Every 1 hour it will rotate the orbit, whereas our navigation satellites took 1 day to rotate to complete its orbit. What does the navigation satellites do? It is like your chit chat friend. It will be always talking. What to do? Television and mobile communication. All those things will come under this navigation satellites and weather forecasting also. Whether I have to go out or not. If your friend is asking, you will see weather and tell no. Same thing this navigation satellite also will do. Apart from that navigation, whatever I told about this, that is communication satellites. Navigation satellites are like a GPS, GeoSPS. It will give you that you are having a built-in chip like GPS, right, in your mobile. Similarly, our ISRO, we have a navigation satellite called IRNS constellations, Indian Regional Navigation Satellites, which are in the developing stage. Chip is in developing stage. So like GPS, your all Android and iPhone will be for the future. It will have a chip of IRNSs that will give you precise, accurate thing, which is 0 to 10 meters of accuracy. So coming to, apart from that, we have a space exploration satellites. What are the space exploration satellites? These are the real satellites which give you research about the interplanetary missions, like Mars orbiter mission, Venus orbiter mission, and your Chandrayaan lunar orbit. All these things will be covered under here. This is like NRIs who go abroad, taking photos and sending data to the home. And we are thinking of, correct? So these are the prime centers, prime things we are using. Whatever we discussed, that has been classified here. Earth observation, that is Indian remote sensing satellites. These are the satellites which are in on orbit by our Indian government. So communication satellites called INSAT, GSAT, regional navigation, I said IRNSS. This is the constellation where IRNSS will give. Accurately, three GPS satellites are required to give you a precise accurate location. Similarly, IRNSS also at the same time, any point of time, 3 satellites should be in loop to give you a pointing accuracy. Similarly, scientific observatory. This is AstroSat, Aditya. These are all for scientific experiments to see about sun atmosphere. Interplanetary, Mars orbiter mission. So that is my first interplanetary mission which I worked and got ex-scientist award. Coming to lunar orbiter mission, Chandrayaan 1 and 2. Lunar landing, that is Chandrayaan 2 which is landed, Chandrayaan 3. And rover is for Chandrayaan 2 and 3. Earth re-entry, object which is in space, then we have recovered through flash. So that is SRE and crew modules. This we have done. Coming to space docking, we have recently launched and exercised the space docking mission, SpaceX. Coming to human space flights, Gaganyaan, which is going to fly in 2028.
The spacecraft and the satellite are the same, or the spacecraft is only the carrying vehicle?
No. What I mean?
Spacecraft and satellites are spacecraft?
Both are
only
same.
carrying vehicle?
No, spacecraft and satellite both are same. Spacecraft as a whole, satellite means only control algorithms and control actuators will come into picture. As a spacecraft, if you say, that is a whole, which includes payload, which includes complete structure is called spacecraft.
Not the carrying.
Not the carrying.
PSLV, etc.
No, PSLV is a launch vehicle.
Yeah, I thought spacecraft.
No, spacecraft and satellite. So coming to axis definition, spacecraft having its own axis called yaw, roll and pitch. So this will give you the stability. I will explain you through the next slide. So this slide is the prime things which covers all the spacecraft operations. If you see center onboard computer, OBC is the onboard computer. That I told you in the very beginning, we need one brain. So brain has to work precisely to sense and actuate it. So brain is having one controlling software that is residing in this onboard package, which is interlinked with this. These are the sensors which is in left side. Okay. Assume OBC. OBC is where you are giving a exam. Okay. Your eyes and ears are your sensors, which is listening every environment things and you are giving. And your hands and legs are the actuators, which is actually doing the work. But what to do, how to do, where to write, everything will be decided by your onboard computer. That is called brain. Okay. So onboard computer is having its built-in onboard software within residing it. These are the sensor things and these are the actuator things. What are the sensor and actuators? The magnetometer, star sensor, sun sensor, earth sensor, gyroscopes, everything we are coming under the sensor. What these are all really do? Example, star sensor. In spacecraft has its own orbit to rotate it. But that orbit should not miss its orientation. If I am walking here, my eyes has to lock one position. That position will be keep on gradually moving when I am moving progressively. Same way, star sensor will give one orientation that will see the star and star pattern will be noted. If that star pattern, if for example star pattern, if it is in the star symbol, that pattern has been locked by the spacecraft will never miss that pattern. If it misses means it changes its attitude. Once again we have to reorientate the spacecraft to fix the star position. Why it means if spacecraft if it is in this position, that position will never should be changed because all payloads everything will be categorized in that same position. Correct. So that will be precisely tells by your star sensor. Sun sensor. Sun sensor what it will do? Sun sensor. One of your any of your friend who have a tan effect, he will tell that sun will be which side. I will not show my face to that side. Similarly, our spacecraft also sun I have to point to get the energy from solar cells. Solar cells has to point the sun always. So sun sensor will drive automatically which side the sun is in the 360-degree belly band. So it will rotate, keep on, and find the sun and putting the sun into the solar panel towards the sun to initiate the charging. For that, sun sensor is used. What is the earth sensor is used? Earth sensor always look for the earth because all telecom and telemetry, what I am communicating to the spacecraft, that should reach the spacecraft. What spacecraft is giving back, that earth has to receive. Which means earth antenna should be always pointing towards your spacecraft antenna. So how I can make such that in spacecraft frontal view or whichever view is pointing towards earth, I am putting earth sensor, I am placing earth sensor in that position. So it is keep on watching like IPL highlights in a loop. Oh yeah, we have to lock it. If it missed earth, spacecraft is lost. So this sensor will give you for that purpose. Gyroscopes. Gyroscopes is a design. It's like a dancing dog in the spacecraft. What it will do, it will keep on rotating. Means it's having its own wheel inside. It will keep on counting that how fast spacecraft is rotating, on which axis it is rotating. So spacecraft is moving in a 27,000 km per hour speed, assume, or 4 km per hour speed. So 4 km hour per speed, whether it's 4 km or not, which is who will define that? This gyroscopes will derive it. This is dynamically tuned gyroscopes, which always with the incremental speed, it will detect that what speed spacecraft is rotating, on which axis it is dancing. So if you your onboard software will detect that angular velocity. Based on that angular velocity, it will correct the spacecraft. And magnetometer. Magnetometer tells that it's a Desi compass thing. What it will tell spacecraft by earth magnetic field, it sends the magnetic field and tell the directions. This side is north, that side is east, this is west. You have to tune now spacecraft towards the east. All these things will be sensed like this. And actuator will do actuations. What it will do, these are the wheels. Wheels are continuously read by the OBC. Wheels is like continuously rotating wheel. That's like it is doing yoga in your space. What it will do, it will simply do yoga. If anything mismatch is there, it will correct on its own by balancing. If all wheels are getting jammed, that is, then you will be go to Sarvasana only. You will lost. Wheels is the prime suspect of actuator. It will control the spacecraft from the error correction, means attitude correction. Coming to thrusters. Wheels will reduce small attitude corrections, but I want to do orbit trajectory. Means now I want to put a spacecraft in a 36,000 kilometer orbit, but my launch vehicle will not have doesn't have a capacity to brought my satellite into and putting into the geostationary orbit. It will put in the geotransfer orbit. How much capacity of my launch vehicle? That launch vehicle will put spacecraft in that transfer orbit only. From transfer orbit, I have to fire the spacecraft to geo orbit. That is desired location. We have to pull. How we can put wheels will not sufficient to brought back the everything. So we need a thrust. Thrust is like if you are going to gym, you have protein, correct? Protein powder. When how much you are taking, that much fire you will do work out. Correct. Same way, it's a small fire will fire everything. Entire spacecraft will be pushed to different orbit, and finally pushing till leads to the target location. That is the thrusters. Magnetic torques are small corrections. What it will do based on your magnetic earth magnetic field, magnet to magnet it will find the thing and slight nudge it will correct. So these are all for small corrections. Wheels is for up to some level of major corrections. So, and thruster is for orbit raising and maneuvering strategy. So, all these things are interrelated in your onboard computer. So, computer has to read the stars, all sensor data and actuate it accordingly. Got it? So, there are a lot of researches. How you can think of why this many sensors are required, why one sensor we cannot manage. All sensors are not, we always assume that all sensors are not in loop. You have all sensors. Here you have sensor, nose you have a sensor, eyes you have a sensor, but all are not for made for same. They may be interlinked. Whenever spacecraft is lost its control, first primitive thing is it has to control the spacecraft from the determining stage to the non-determining stage and first to find the sun. So for that you have always required sun sensor. You cannot replace sun sensor with that sensor. First I have to control the spacecraft. Then only I can point towards Earth. After pointing towards Earth only I can have the communication between the spacecraft and me. Until or unless spacecraft will be in lost only. So whatever we discussed, all these things here, sensors and actuators, what it is means and why it is used for. And attitude control algorithms, this will be more, you have done in pit controller or any other things. Anybody is from electrical background here? Sir, okay. So attitude control algorithms, sensors will give, sensors received attitude will be computed and attitude control algorithms will sense it based on the sensor elements it will define and actuate it. So spacecraft dynamics will give the negative feedback. That negative feedback will be computed attitude. Again, it will be loop back. So this is like simple control system algorithm. You know attitude dynamics and kinematics? Orbit dynamics. Orbit dynamics is what? Spacecraft is there completely rotating towards Earth. Correct? So orbit dynamics will tell that where I am, where I have to go. Position and velocity it will precisely tell. So it will be position velocity of the orbit control. There are so many orbit are there. Any one circular orbit, inclination orbit, all those things. Circular orbit is like how you can define circular orbit, like your semester exams. Your topper will always score more than 90 marks. So there are that is fixed. Your topper means they will always come under S category, satisfactory. So that is all circular orbits, like your semester exam. Whereas inclined orbit, like your internal mass, up and down variations will be there. So inclined orbit will be there. So both will be essentially gives the position velocity, which is used for orbit control, and always you know that F equal to L of acceleration. Whereas attitude dynamics will give how much attitude I have to rotate the spacecraft. It is like taking a group selfie. If one person is look away, you can retake. But everyone look away, spacecraft lost. Mission lost, accomplished. So attitude determination and attitude control will be tau equal to J moment of inertia dou omega by dou t. Okay, this is fixed things. Okay. And software architecture, all our logics are completely scheduled in according way. Everything will, this is the infinite loop which is running on the onboard computer, and everything will be infinitely running, keep on running in a 128 millisecond or 64 millisecond frequency. Every 64 millisecond frequency, I have to complete my operation. Then only I can give the spacecraft to control. Mind will precisely notify how much in nanoseconds you will take a decision. Same way, at least with the jitter, 64 milliseconds, I have to give a proper output from sensors to actuator. Then only my spacecraft will be in control. So all these things will be scheduled accordingly. This is like the round robin thing only. So all modules will be scattered based on the time, memory, things. We have so many autonomies in our onboard. Why autonomy is required? We are always placing main and redundant. Two sensors will be there. Even OBC also, onboard computer also, main will be there as well as redundant will be there. If one fails, automatically it has to switch over to the redundant with no time. So which means I have to predict my failure very a priori. So from now, wheels are going to fail based on the wheel health information and wheel data. I can predict that so and so time my wheel has to be get failed, so I have to switch over to the redundant wheel. All this FDR, fault detection in isolation recovery logics are built in on board. It will keep on enable, and any time it will be changeover will take place. How this AOCS elements are getting tested? Sorry, sir.
What is achieving this? How many processes?
Sir, actually for this, very light process. It is not like Intel or nothing. If you take HX1750, for me I know what time this has to read. So HX1750 processor for a 16-bit microprocessor is used.
How many?
Only one. Only one for.
Fault tolerance.
Means?
Fault tolerance. If one fails,
always two. Fault tolerant, always look for two. Main and redundant. If main fails, I have to switch over to the redundant. Main recovery will be parallelly doing, but main will not recover. Means always all objects in the spacecraft we are having redundancy. That is single redundancy, not multiple redundancy.
but for LCA, three processes.
Which one?
For LCA, three processes.
Where?
In LCA, onboard.
LCM. We have two. Everything is two. Onboard computer also two, which is having single processor and a redundant one single processor. So how we are test the spacecraft of AOCS? Testing using simulation models. First start by unit testing. Module by module will get covered. Then integrated software testing, complete software at once. And oils, onboarding loop simulation. That is flight compatible sensor and actual models. And hills, hardware in loop testing. Then integrated spacecraft level testing and in-flight testing, on-orbit testing. So major achievements wise, this is 2004 Mars orbiter insertion. So from the Earth trajectory, slowly it is ground trajectory and then it reaches the Martian orbit. This is a Martian orbit, not a Martian lander, which is done at September 24 in Mars orbit insertion. So this is the splash things, crew module, which is splashed down in the Bay of Bengal and it is recovered back. Crew module for after 7 days of orbit thing. Then we are in the development of Indian nano satellites, which is 5 kgs of satellites, only for academic purposes. So this will be launched in a sun-synchronous orbit. This is the inclination sun-synchronous orbit. Always this will be, equator will be in the Bangalore region. So recently Chandrayaan 3, whatever launched from the insertion orbit, earthbound nodes, after earthbound nodes crossed, lunar orbit insertion, then it is in lunar orbit. So corresponding spacecraft view using what GSLV Mark 3. So this is our first time Mars orbiter time, what our scientists or what our crew members got. Okay. So this ends with my presentation. If you have any doubts, let me know.
The space requirements are much stringent than the airborne systems.
Correct, sir. We have different domains because yes, as you said, it's very stringent. Why? Because like inside kind of satellites, there are communication satellites. Their requirements will be almost frozen. So this is the payload, that is the modulator how you are going to use, what are the TTCs you are going to use, everything will be fixed and give you some idea. So you can design and develop spacecraft in 1 year and deliver. But in case of remote sensing satellites, payload is different. We don't know the operation of payload in on-orbit on such scenario. And we have only 10 minutes of time, passing time, between LOS and AOS, acquisition of signal and loss of signal. Because every 1 hour that orbit will be reduced, 600 kilometer orbit. Bangalore region, it may come, only 10 minutes we can be in control. Apart from Bangalore, we have to Bayak, Indonesia, we have to take, Mauritius, we have to take, like this. So everywhere you have a 10 minutes time only. If any problem occurs, out of this 10 minutes, spacecraft will be lost. So many autonomies we have to build in, such that if any anonymous conditions, if satellite having any such issues, it has to recover back. So these kind of stringent issues are very challenging task in front of IRS. And the country needs IRS satellites only because for safety and security. and interplanetary. As you know, in India, IRS missions we know the orbit, INSAT missions we know the orbit. But in case of interplanetary orbit, everything we have to control and we have to predict as much as earlier. A single, this bottle weight also causes a mass huge in center of gravity, and orbit accordingly it will change. So all those studies, simulations, everything is crucial task.
And the real-time simulation is at 64
Millisecond. 64 millisecond for wheel modes, thruster modes 128 millisecond. Because thruster we have a slight and control, we can tell that how to push, when to push. But in case of wheel mode, 64 milliseconds is very stringent. We have to deal with that.
The process are
Process are much capable. That's what. This is if here memory management is not there. Only input and output, sensor and actuators. So we will not use processor for any other level. Only input and output processor. For that only embedded.
are there any Indian processors? No.
HX7, as of now, whatever satellites is flowing with not Indian processors. All our means our Indian processors are not space sovereigns on our things. So we have to go with the ESA, NASA, whatever they are.
Thank you for that enlightening session, sir. Now, with great pleasure, I invite Dr. Prahlad Rao, sir, R&D head, to lead us into the next session.
Good morning. Morning. So it's an excellent talk, sir. Thank you very much. So, actually, we worked on the onboard computer for the Agni missile, Agni ICBM in HCL Hyderabad. Then also, I was in the NCA program here in the definition phase. I came to Bangalore for working for 1 year with the NCA program, but went last 36 years. Okay. So basically, I was having an ambiguity till yesterday what talk I should do, whether it's on AI or it's quantum computing. But that's why I keep on asking Madam, what is the program agenda and all that. Okay, but initial original I thought somebody will be taking care of the AI related. So, but I thought, okay, then final night only I converged that let me talk on the quantum computing and then, okay. So, so today if we see that computing underwent a lot of phases, right? And almost like every 5 years, the computing paradigm shifted. Okay, so initially we had forget about the initial phase. Let us talk from the high performance computing stage. Okay, so parallel computing itself is a big jump in the computing this one, and then we from parallel computing we went to a the realization of the parallel computing which serves a big task, and we thought of cloud computing, cluster computing, then grid computing. Hello. Cluster computing, grid computing. Then slowly, when we were working on the grid computing, we found that the number of processors in the grid are not sufficient. We were having a Garda project. I was there in that, and we were having almost 2,000 servers on the grid, but that was not sufficient. Then 70 organizations are the partners of this project, like ISRO and all IITs and all that. Then the spin of the grid computing was the cloud computing. So cloud computing started only in 2007 and all that. And then slowly, then when the cloud was a reality, then a lot of data is there, and big data evolved from 2012 and 2015 timeframe. Then IoT field got evolved like that. So computing field is getting evolved. And today we are talking about AI-based machines and all that, the GPUs and all that we are AI. Okay. So now this quantum computing, I keep hearing it when I was in IBM 2000 to 2004 time frame. We used to do these quantum computing, the quantum computing related discussions and all that we used to do. IBM was also in that quantum computing. At that time, really nothing was there, but we were doing some think tank discussions and all that. So now today, if we talk about quantum computing, it's a lot of huge information and a lot of huge industry is working on that. Government of India also now pumping almost 10 to 20,000 crores into the quantum computing mission. And put any projects, proposals, you're likely to get. Okay, and not only the government of India, even Google are planning to bring out its quantum computing, 2000 bit qubit computing, and everybody, Microsoft, everybody is now, it's a big race going on the quantum computing race across the globe. So I'll just give a little overview because my time is 45 minutes, Madam, but otherwise I have a session for 1.5 hours, 2 hours session. Some of the things I will not explain. Basically, later we can have it for the faculty here. Okay. Okay. So basically, many of you are maybe thinking that why that quantum computing is so important today, and what is different. All of us understood the computing. We are very well understood computing algorithms, computing technologies, hardware, operating systems, languages, and so on and so forth. But how this quantum computing differs from the classical computing, those things I just wanted to mention. Okay, so these are some of the points which I thought of presenting. Okay, so I'll give an introduction, a little bit of differences between the classical computing and quantum computing, and how the quantum gates, quantum algorithms, and little bit, and what are the various important applications which can do it, which otherwise takes millions of years on a classical computer to solve. Okay. So these are some of the references you can have. Okay, I thought of this. I'll skip it because it's all physics and all that comes. So we know that classical in physics sense of classical mechanics, theory of magnetism, and this one. See, in the classical computing, classical mechanics and all that, everything is perceivable, measurable, definable. But whereas if you go to the quantum computing, right, it's unpredictable. So that is where the quantum field differs from that, right? So the successful classical physics, all these things we are seeing that from the classical physics, certain things changes that you cannot properly define it, whereas in the relative domains and at microscopic levels. Microscopic levels means that is what the quantum field will just define what it is. And also you might have heard of the Moore's law, right? And we thought that Moore's law is going to converge in 2012 time frame, and then no more. That means basically the computing power keep on increasing, double every 1.5 years and all, or 18 months and all. That's the Moore's law. And 2012 time frame, that is almost like a saturation state and all that. That no more faster and all. But still, the Moore's law is applicable today. Okay, I just talk about that. And the classical computing, we know that, all of you know that. So there's the peripherals, computer and communication interfaces and all that. And inside the CPU, main memory and input output. So all of you know that. Okay. So then it is a simple, small application. Like suppose that coin game in a casino, that you might have seen that many of you might have visited the US and all that. There's very popular place in Las Vegas. Everybody go there. When you go to US to play at least some time in this casinos. Okay, the computers can play with the humans. Okay, and starts with a small example. Small this one. Say it's a small coin tossing. Okay, start with the head of this one. Here the computer will play, and here you can play. Right here you can play, and after that, after again computer plays. At the end of this one, you should say that whether the coin is head or this one. Okay, this game with that is a probability that 50%. If you say that if you put some money on this game, if it is a head or this one, likelihood that you will get win is 50%, right? But whereas if the quantum computing can play that, I can win it with 100%. Okay, how we win that? We just look into it. Like that. There are a lot of examples. Okay, now let us see that. So what is the quantum computing? The quantum physics basically talks about the at the microscopic systems, like basically atoms and subatoms level. Okay, electrons, protons, and all that. The quantum computers operate behaving of these quantum particles. These are the quantum particles. Quantum particles is basically these subatomic particles. Okay, atomic and subatomic particles level, what we call that. Okay, so they operate at the quantum level. So the quantum computer is looking for a powerful version, like classical computer is basically doesn't like that. Okay, the bits means we know that bit has the whereas a quantum bit you cannot predict that. It is in both zero state as well as one state, superposition state we can call it. And only when you do the measurement it collapses to one value. Okay, that will take it. Just like the quantum computer and comparison effect you want to that. Quantum computers and classical computer, it is altogether is a different technology, different way. Like suppose I have a candle bulb and then I want to get the same amount of light using the candles, right? So instead of electric bulbs and all. No matter any number of candles you put that, you cannot achieve the electric light intensity and all. Okay. It's altogether a new type of devices which works on the quantum mechanics. Okay. So the quantum computer differs from this one. It uses the laws of quantum mechanics to perform the massive parallel computing through superposition, entanglement, and decoherence. These are some of the states of the quantum particles which are being used in the quantum computing. Okay, that say classical computers, you know that like voltages and all that. Everything is a known state. I can measure it, the bits, patterns, and all that. Okay, at every state, it will not be like a random. Okay. These are about the previous example. Okay. Now, what is a quantum bit? Some of the slides I'm skipping just for the sake of so that I can cover it. So the quantum bit is the smallest unit of information in the quantum computer. Okay. So it represents the state of a wave function. Okay. It's a Schrodinger's equation. It's a wave function basically. A qubit can be in on state or off state. So if you can say on state is 1, like similar to the classical computing, and off state is 0, that means it is representing 2 bits. If it is representing 2 bits, it's say qubits, right? Okay. So the 2 states of a qubit are represented by vectors. Vector notation is the Dirac notation. So they can how to implement these bits. If it is in computers who use a storage device, right? That flip flop is used for representing the bits. That's how the memory and all that built. But whereas here, this bit can be implemented either the spin of the nuclear magnetic resonance. That means if it is spinning clockwise, maybe it can be 0 state. Anti-clockwise can be other state. Or if it can be photons cavity, if it is a photon is there, a 0 state and 1 state, or it can be energy state like a ground state and excited state. Like that, the implementation of these qubits can be many ways we can do that, chemically or physics based or some device. Okay, so this superposition is always described as the same state. Okay. Okay. So quantum computing is laws of this one, quantum mechanics. We have seen that. There are very powerful properties which are being used in the quantum computing. What is that? So the potential applications is like quantum uncertainty, which is being used in the like private keys. People have seen that. We all might be aware of the Shor's algorithm and all that, right? So today we can realize the security things using the quantum computing, which takes almost like with the most powerful supercomputers to break the key. It takes 10,000 years using a 65,000 or 1 million processors at the same time and all. So that powerful actually, right? So to break the basic laws of quantum physics take like hacking. Right now we are using this some of these systems. Okay, so it takes almost more than 17 billion connected devices globally and all that for decryption. Okay, now next is molecular applications, bioinformatics side, right? So it can be used in the healthcare and medicine. In the drug design, medicine we are using the drug design. Drug design, people will be using the massive supercomputers, massive parallel computers. Okay, basically the design and analysis of molecules for drug design is a challenging problem today. Basically because exactly describe and calculate the quantum properties of the atoms in the molecular. So if you're using the classical computers, what we do is it needs a lot of computational time and the number of bits and all that. Okay, but for a quantum computer to do it, it operates with the same quantum properties and it uses very less number of bits and a process. Okay, so future, you know that for Alzheimer's diseases to decode and all that, the blue brain computing project. Have you heard of that? Blue brain computing. See, now in the world is able to do big science experiments. We are able to today think about that because of the powerful computing available. Big science experiments. There are so many big science experiments are there. One of them is the Blue Brain project. Basically, there were almost like 147 countries are collaborating in this project, and in Sweden or somewhere they are working on that. Similarly, we were having also the cryogenic this one, right? Big Bang theory. Big Bang, right? We know that whether the Earth has generated by the Big Bang. That's also LC, Large Collider Hydra, LHC project. Like this is also a big science project. Almost like 100, 200 countries participated in the project and all that. So after the grid computing became a reality, people started able to take up these big science experiments, right? So there are a lot of big science experiments which are happening. The outcome of that is what big data and all that, data science and all that. Okay, today. So the future large scale quantum simulations, regulatory, etc., is possible today. We can do that. And brain computing. There is another big science experiment is brain computing. They wanted to map the human brain totally, understand its functionality, and then design chips. We call it as brain chips, right? That people are working on that. All advanced institutes are working on that. Okay. Next, the teleportation. You know what is the teleportation? You might have seen a lot of star movies, right? Star movies, right? What is it? Star Trek and all those movies, right? People will be vanishing from here and going into this one, and also from anywhere to anywhere, I can instantaneously communicate. These are all teleportation applications. It is not possible by the classical computing. It is possible by the quantum computing. How? If I can take two qubits, entangled qubits, okay? These qubits, if I can take it into space, any distance, infinite distance, okay? These two entangled qubits from anywhere, if they'll be in the superposition state, computing state, but when the measurement I do on one of them, I can predict then this superposition etc. collapses at that. Whenever you take measurements on the quantum computing, it collapses at that time when it interacts with the environment basically. At that time, I can say that if I want to communicate something with that, if it is I wanted this point as a 0, I can make that point as a 1. Instantly, you take it in the galaxy any amount of distance. This entangled property is preserved. That's where the Einstein got what is that surprise? How it is? It is some spoopy operations which he was initially in 1947 and all this. The quantum physics is rejecting it, but after some time, then today it is possible. That means there is a theory of relativity and all that fails to explain this type of things, right? Okay. So sounds like scientific fiction. In such a way, when you change something about the particle, that is the entangled particle, it can impact the other one. This is what the teleport is. Right now, we are trying to experiment it, use it in communications. And the current state is that they are able to do this teleportation in a lab environment, few hundred meters and all that. But one of the experiments they did is they put one of the entangled particles in the spacecraft and taken to larger distances, and they found that this is true. Okay, so the teleportation is already being demonstrated in research labs as well as in one of this graph. It could be part of future internet. So now internet, this no matter where it is, it can instantaneously communicate, right? No matter it is even in the Mars or on the Earth, right? Between communications, right? This is the future internet. We don't have such network today, right? Okay. And okay, quantum classical computer is a state at a time. One state you can properly define. But whereas here, you cannot properly define that at a state. Their states are in superposition state and they are entangled state, and there will be interference between one state to the other state and all that. Okay? Many states will be in a continuously execution state. So like, say, we know if it is 3 bits, we know that what are the various possible states in the classical computing, 8 states and all that. So if it is a 3 quantum bits, these states can be continuously in infinite number of states, multiple infinite number of states actually. Which I talk about that each of the bit and all that I talk a little bit. So okay, this is the evolution of quantum theory and quantum technology. If you see that, say they're from 1928, Dirac mathematically showed that the 2 states of the wave function he is able to represent it and all that. Then the Schrodinger's equation proposed in 1900. 1935 as the EPR paradox. Okay. Then Feynman experiments in 1965, and then between 1980 and 20, you see that some theory to practice. Basically, so the first quantum cryptography is demonstrated by IBM in 1984, and then we have made the Shor's algorithm also being all that executed on the quantum, and we are not able to say decrypt it. Okay, using the quantum computers fast, but in the normal computers it's very difficult to decrypt. Okay, so in 98 first 2 qubit quantum computers came, and if I go to 2004, okay, there are entanglement arguments. This is the 2010 D-Wave announced the first commercially available quantum computer. 2010. This machine I have seen it in 2007. We went to supercomputing conference in US. So they demonstrated it. The CPU should be maintained with the cryogenic system. Okay, and then 2016 IBM made the 5 qubit quantum computer available, and 2012. If you see that, a lot of it developed. 2012 January, D-Wave makes the 2000 Q system. They announced that commercially available system. See, up till this time, the commercially available quantum computers are not there. All people are working, but they are not able to really make it a hardware. Okay. And 2017, IBM announced a 16-bit Q machine, and then in 2017, Microsoft reveals a quantum programming logic, and then 2017, Google announced the open source chemistry package for quantum computing. And 2017, IBM announced the 20 qubit machine. Okay, and 2020, if you see that, now if you see that Google claims that their quantum supremacy they have demonstrated, and IBM is talking about 2-bit. Today we are talking about 2000 qubit machines and all that today, because recently in the last year I attended a quantum computing workshop in the they are saying that IBM people and all that there. And Google also bringing out its own 2000 qubit machine. Okay, let us see. If if you brief history, if you see that these are all the basic initial states of the quantum related theories are done. From 81 onwards, I'm talking about middle of this one, right? First universal quantum computer is designed. Then first quantum algorithms were announced, and qubits, quantum bits, and all the realization, etc., being identified. So first they prepared a qubit with techniques, right? There is a collaborative project like Oxford, IBM, MIT, Stanford, and all work. Then in 2000, quantum computer of 7 bits based on the NMR, last almost labs they did that. And then like that, if you see that quantum dots is today reality, exponents in the quantum photons. First realize the quantum bit using the photons, right? Here, this is that. Okay. And then D-Wave, they announced the first commercial quantum computer. Okay. Then same D-Wave in 2012, 84 qubits machine, and 2000 qubit machine in 2017. Microsoft started in 2007. Q-Sharp is the quantum computer, the quantum computer chip. Google announced the quantum chip of 72 bit, and Google actually they said they demonstrated the quantum supremacy like 54 qubits, and this encrypted algorithm, if I do it at normal conventional supercomputers biggest, it takes 10,000 years, which they showed it in the quantum computing. They decrypt it and all that. Okay, so in 2019 revealed 53 qubit machine, and Chinese also started working that, and 100 trillion times the time of a classical supercomputer. They are able to realize that, and these are race. By 2030, IBM Q computer says that will announce the 1 million qubit quantum machine. Okay, so now all companies, is there a huge rush on the quantum computing research globally, and also government of India also realized, and last year, 1.5 years back, they announced almost like a 10,000 crores for quantum computing mission. Okay, so the quantum computers look like this. Some of the quantum computers, Chinese 76 qubit machine quantum computer. This is the ion cube. This is the ion trapped quantum computer. The hardware, how they realize that. This is a cryogenic based quantum computers. So that means cryogenic means basically the CPU has to be maintained at minus 273 degrees centigrade. Okay, like normal our classical computer, we can put it in room temperature also, we can work. So that's a big challenge, right? Okay. So the quantum computing race is almost like that. A lot of R&D investments and all that. Almost 10 billion by 2024, and also not only investment, there are people are earning that. Okay, huge potential, right? European Union also they are investing by year 2022. There are so many hardware. These are all the hardware realizing computers companies, and then materials, etc. These are the various companies. Operating system people are working very few. Just see that. Okay, and then applications. There again multiple people are there. Right. So this is the quantum mechanics is a theory that describes the behavior of microscopic system. Now let us get into that. What is this technology and how it's being? Not much time because I have limited time. Okay. So it's basically we talk about the microscopic this means photons, electrons, atoms, molecules, subatomic particles like what. Okay. So quantum mechanics sometimes look like an assorted mix of weird stuff. There is a wave particle. This is a wave particle duality. We use that. So that means the quantum bits can be in either state, 0 state and 1 state at the same time. But whereas in our quantum or non-classical computing, it is only we know that state is fixed, right? So even the Richard Feynman said that nobody understood the quantum mechanics at this point, even today. Okay, but it works. We talked about so many movies we have seen that multiverse. Have you heard of that? Multiverse. There's similar universe is existing elsewhere in the space, and there are something like portals in some of the movies we have seen portal, right? The time collapses, right? From one plane to the billions of miles distant planets, you can travel in no time, right? The portal. They are all reality today. People are trying to get into that, right? People are trying to do this travel and all that. Okay, so So now you're not going to be able to understand it. Right now, in this current state, we are not able to understand how this quantum world behaves, quantum world predictions and all that. Okay. The theory of quantum electronics nature as observed from the point of view that common sense. They also say that similar to you, there are 7 people in this universe. They will be exactly thinking like you. Forget about the universe, in the earth itself. Okay? The physicists predict that. Similar, that's why when you are doing a research, no? Suppose you start working for your PhD, your PhD will come out of 5 years, right? You will see that at the end of the 5 years, there's somebody who will be working the exactly similar PhD like yours. I encountered that in my 1995. What problem I worked? There was somebody who announced a paper in 1995 in Calcutta. He was working exactly the same problem, and that guy came to our professor in Bangalore, and we had similar things. Okay, these are the challenges, basically. Okay. Okay, so the one bit representing the classical bit is 0 state, 1 state, and all that. But whereas in the quantum computer, which is a Dirac vector, this Dirac 0 is defined as mathematically, like you can show that, and 1 vector is that. And identity matrix is a matrix which will be, you can transform one state to the other state, basically using this. Okay, so like we have shown that here. Here you can 0 can be converted. That means like inverter gate, you can 0 vector can be converted into 1 vector using the inversion gates and all that. We'll talk. Like for here example, the basic operations in the quantum computing is identity operation, negation, constant 1, constant 0. Like not only 4, there are multiple. I'm just demonstrating what it means. That means f of x is equal to x. The function can be realized by the identity matrix, like matrix. I am showing that, and this is the vector. Okay. If I apply it to 0, 0 is apply function of identity, then it becomes 0. 1 identity f of 1 is equal to 1. Correct? And then negation, f of x is equal to minus x. Okay? That we can realize. I can show that with these vectors, how I can do that mathematically. Okay? So similarly, constant, f of x is equal to 0 always, f of x is equal to 1 with this vector notation of the Dirac vector and all that. Okay? The classical mechanics ideally deals with the microscopic particles. We have seen that. It's based on Newton's law of motion, Maxwell's electromagnetic wave theory and all that. Any amount of energy may be emitted or absorbed continuously. The state of the system is defined exactly by specifying the positions and velocities. Okay. The future state can be predicted with certainty. This is the beauty of this, right? You can predict the future state, what you want. We'll see. Sure. In the classical mechanics, but whereas the quantum mechanics, it deals with the microscopic particles based on the Schrödinger equation, etc. Only discrete values of energy. Energy here is continuous in the classical systems, whereas it is a quantum. Quantum is packets, basically, right? Then Heisenberg's uncertainty principles and all that work on that. Okay, that is on the. They showed that on the wave, right? The particle and wave. Each same particle exhibits the property of a particle properties as well as the wave particle. We have seen that. That's why the Newton's theory, the collapse, right? Newton thought that all particles always will traveling in a straight line and we have the reaction and all that. Okay? In the quantum field, basically that not only that particle travels, along with the particle also exhibits this one, the perpendicular direction, the wave transmission and all that. Okay? So it gives probabilities of finding particle at various locations and all that. The quantum bit can be realized by any ways. These are various ways I'm showing that. Google has realized that by the superconducting loops. Okay. Then Honeywell and EonQ, they realized that trapping in ions in a particular state. And then Intel has realized the silicon-based quantum bits. And Microsoft was talking about the topological paths. Okay. The quantum bit is the basic fundamental information in the quantum computer. It represents the state of a wave function. Okay, the wave function which follows this Schrödinger equation. A qubit may be in on state or off state. If it is a qubit, okay, there are 2 states. Qubit means it exhibits 2 states. But whereas is a quantum dot, each bit can exhibit infinite number of states. We'll talk about. The 2 states of a qubit are dependent on 0 and 1. Many ways to realize that and all that. And superposition is also one of the property of that. We will skip some of this. Okay. So if you see that general form, the qubit is defined. This is a wave function we call it as. Okay. This is a wave function. We can define that. And if you see this, the qubit biosphere is being defined here. So this one we call it as zero state, and this is one state. And every qubit will be in the entangled state, right? And in a superposition. That means each bit can be, it need not be only 0 state or 1 state. I can define infinite number of states for each of the qubit. It can be here, it can be here, it can be here in the space, right? In space, how many points are there in 3 dimension? Infinite. That means I can define on a qubit infinite states on that. I can preserve those infinite states. For qubit can be used to represent the infinite states, right? That means in a classical computer to represent some states, right? Suppose I want to 8-bit state, I need to have 3 bits. I know that, right? 2 to the power 64-bit computers, 128-bit computers, etc. Here is 1 qubit, I can read this, those states. Okay. So this is a normalization condition. Alpha square gives the probability. That means I can say that this is the equation, right? Wave equation. But if I can say that what is my state of 0, at that time I can say the probability of 0 state will be alpha 0 square, and probability of 1 state is alpha 1 square. Okay, so this is the normalization condition equation now. We can predict the state of a particular qubit. And classical gate, like we know that NOT gate, AND gate, OR gate, and all that, electronics and all that. But whereas in quantum computing, there are few gates like poly X gate. What it does is, so when you apply this transformation, like this X is represented mathematically, if you represent this poly gate, this is the vector. So when I apply this poly gate X, so the operation applied on 0 bit will become 1. Okay, operation applied on 1 bit becomes 0. This is equivalent to our NOT gate. You are realizing a Boolean NOT gate. Okay, like AND gate. Okay, so like that, this I can design the gate here, and okay, and another difference between the computers and quantum computer is quantum computing operations are reversible, whereas classical computing is irreversible. Right? Suppose if I know the value of here this one, I cannot I cannot again generate the states of B1, B2. It is irreversible. But whereas here, suppose this is one state of your quantum state. To generate the previous state, I can apply this operation on this, and again I can go back. This is another important property of a quantum computer. Okay, operations are reversible. Okay. So the transformation of generally basically in the every quantum computing, you have initialization required and state evolution, the process it has to go, and then when you want to do the measurements, you have to do the measurements, right? So at that time, when you are doing the measurements, the whole system, the quantum system operations collapses. That means whenever you leave it, that it will keep on computing state in the infinite amount of time. But when I want to do certain measurements and all that, at that measurement state, all the quantum bits, okay, they collapse. That means we can, if I define on certain quantum bits some state, I can predict what is the value of the other bits. Okay, this is what this is a normal flow of the quantum computing both. Okay, so unitary transformation is okay. On quantum computer, programs are executed by unitary evolution. Okay, all unitary operations are reversible, right? So this is one of the another important property of the quantum computing. Whereas in the classical computing, we cannot reverse one operation. Once you do some operation, you cannot get back to the previous state, no matter whatever you have done. Certain operations are reversible, like AND gate, NOT gate, you can reverse. 0 state can be, you can get it wrong. Not all. Okay, so classical bits can be in any of the 0 or 1 state, can be measured completely, are not changed by measurement. That's why, because in the classical computing, these bits don't change by measurement. That's why we can use it for storage and all that, right? We can copy the bits, we In memory, you can put it in memory, you can erase the operations and all. But whereas in the quantum, so can be in 0 and 1 state, okay, or in any other state in between. This is called superposition state. That is a linear combination state. Okay, that is a defined by the waveform, like alpha into 0, alpha 1 into 1. I said right. That's a wave function. It can be measured partially with the given probability. Any state can be measured with the probability. I can precisely tell what is the probability of the state will be the 0 state. I can give exactly say what is the probability of that one state and all. Okay. And our change will be measurement. Once you measure it, everything, all the quantum bits collapses, right? That's why we cannot use it like memory. This one, it cannot be copied. It cannot be erased. So adding qubits increases storage exponentially, which is very difficult. To do double the power, digital computer 32-bit to 64-bit is a double the power, right? Power of the computers. But to double the power of the quantum computer, 32 qubits or 33 qubits, right? So the power of a computer, we thought that the more the number of bits, we have more off states of the operation. And then when we are building the parallel computers and all that, more CPUs put together and all that. But here, it is the CPUs now, it is the qubits decides the how much parallelism I can achieve and all. Okay. For example, same operation of mathematical operation of 2 to the power of n numbers. That means n is the number of bits. Okay. On a classical computer of n bits, it requires 2 to the power of n steps on a parallel computer. The same operation, if you put it on the quantum computing, I can do it in one step. Okay. So that's our 64-bit binary number. If I do that, 64-qubit quantum computer operates on a space of 2 to the power 64 dimensions. These are the number of states, and these are states of the quantum states possible. That's why I said now every qubit has infinite number of states you can represent and all that. So I can represent with the 64-bit this one, these many states, and that's how even a powerful computing I can do it in no time. So this is a classical Schrodinger cat. Basically, okay. Actually, Einstein said it's all nonsense. Basically, they showed that with the quantum state, the state can be either in 0 state or 1 state. That means, suppose keep it something in a box, a cat. Can you tell that whether the cat is in a live state or a dead state? You cannot predict that. Okay, in the quantum state, if I want, I can precisely tell that whether the cat is in live state with this probability or dead state with this probability. I'll show this is a very classical experiment which a lot of Einstein's theory of relativity, etc., they're not able to explain that. Okay, and he said it's all trash, spooky operations and all that at distance. That's what the teleportation and all that they're not able to explain in the quantum. So every quantum state can be represented by the sum of 2 or more distinct states, mathematically and all that we see. This is the the wave equation for the 2-qubit computer, and I can say whether the state of this computer is in 0 state or 1 state. I can predict with the probability. 0 state, I can say the probability of alpha square gives me probability of the 0 state, and okay. So with the 3-bit like that, I can predict that. So the classical examples, Schrodinger's cat in a black bar. Since both living and dead cats are obviously valid solutions for a laws of quantum mechanics. Okay. So the entanglement properties, that's what I said. Suppose I entangle 2 particles, 2 bits, and increase the space between these 2 entangled particles in the universe any amount of distance. If I do measurement on one of the state, if I know that the state is 0, I can with certainty I can say that the state is 1. If this is 1 state, then I can say that it is on 0 state. The distance can be. So that we cannot get that infinite speed communication in the theory of relativity and all that. Okay. This is what is the entanglement property of the quantum computers. Okay. When a pair of group of particles are generated, they have shared spatial proximity in a way such that the quantum state of each particle of the pair group cannot be described independently other. Both are dependent.
If I know this state, I can say this state. Okay, that's the entanglement what we talked about. Okay. The entangled pair is a single quantum system in superposition of equally possible states. The entangled state contains no information about the individual particles until you do the measurement. Okay. If a measurement is made, the other will automatically collapse. Correct? Until that time, both these particles will be in entangled state, they will be doing the continuous computations. So Einstein called it as something nonsense. But later he realized that the 80s and all that, his theory could not define. Then quantum entanglement, doing something to one of the pair of entangled particles seems instantly affect the other properties. Okay, this is what spatial relativity, instantaneous influences, impossible, he said, Einstein in his 40s, but later he agreed upon that. Okay, let's do some more. Then decoherence. So entanglement is this one. These quantum bits are in entangled states. Correct? Qubits are in entangled states. You do measurement on one of them, the state collapses, quantum computer state collapses, and I can precisely mention that what is the state of the other bits. Okay? This is the what entanglement we define mathematically. Decoherence. That means every bit will be both in zero state as well as one state. This is called superposition. Only when you do the measurement, either it can be a one state or it can be one zero state. Okay? So quantum decoherence is the loss of superposition because of the spontaneous interaction between the quantum system and its environment. So decoherence can be viewed as the loss of information, and the reason why quantum computers have the long way to because this error correction, there is something called operation called error correction. So currently the error correction is one of the challenges in the quantum computing. People are working on that. So preventing decoherence means biggest challenge for quantum. So measurement. So this is the measurement. In classical computing, we can do the measurement on the system. The measurement of your system will not change the state of the system, correct? In classical computing. But it is not true in the quantum computing. So this measurement will disturb that. The quantum system is perfectly isolated. If you isolate it, means don't do the interaction with the environment. It will maintain the coherence indefinitely. Infinite amount of time it will be working back. Okay, a quantum measure is a decoherence process. When the quantum system is measured, the wave function collapses to some state, new state, according to the probabilistic rule that we defined that, right? So if I say this is a wave function, I can say that it can be in zero state or one state. I can precisely mention what is the probability of the zero state, what is the probability of one state. Okay. Yeah, 2 qubits, this one. I can state each one of them like the probability to read the rightmost bit as 0 is the square of this probability and the square of this probability gives the probability of that rightmost bit. This is a 2-bit computer, right? The rightmost bit is 0. So the quantum gate is, we have seen the quantum, we say the quantum computer means we know that how to realize certain operations, right? Like AND gate, OR gate and all that. Similarly, quantum gates are defined on the quantum computers. They are the building blocks of the quantum circuits to build the quantum circuits, like classical logical circuits. And this is a normalization condition. This is a unitary matrix, unitary function. All the quantum gates have their unitary matrix, unitary function. Okay. So the number of qubits in the input and output of the gate must be equal. Why? Because the quantum computing is the reverse side. But whereas in the classical computing, inputs can be more and output can be less. Number of states. Right? If I can put the input of the circuit can be A, B, C and all that, but output can be only one state. Right? Which is not reversible. But whereas in quantum bit, inputs and output should be the same. Okay? Quantum gates are reversed. So now let us see that unitary matrix. We can show that unitary matrix. Okay, these are the in a linear algebra, a complex square matrix is a unitary matrix. It's a actual property of the unitary matrix is U conjugate U is equal to identity matrix, right? So this is basically that what I'm talking about. So for example, we show that this one. These are the unitary matrix realization and all that. I'll skip that. Okay. So single qubit gates. Suppose 0 state, I can transfer it to 1 state using applying this one, like poly gate. Okay, So this is a X is a Pauli gate here. The operation is mathematically. If I represent that, this is to mathematics. If I apply on one zero vector on this operation, if I apply it on the zero, it becomes one. If I apply this operation on one, it becomes zero. That means it's like a inverse matrix, right? Similarly, yeah, that's what we are showing there. This is equivalent to, we represent a circuit here in the quantum computing like this. Then poly Y gate, these are the operations. Then poly Z gate, this is a mathematical representation that. And Hadamard gate, these are very important circuits being realized with this one. And okay, the emerging gate, H gate. So okay, this is the H gate. So this state, this H gate, if you apply that, this goes from zero state to this state, one state to this vector like this. Okay. So if I apply on this Hadamard gate, you get zero state. Similar reversible. Irreversible is said no, right? No classical computer can do the equivalent part. Okay. So after the qubit 0, 1 and all that, so this is the Hadamard gate. H inverse is equal to H square is equal to identity. This is the property of that. And you know the deterministic power. And C naught, control not gate. Basically what it means that if the control qubit is equal to 0, the target qubit is the same. Right? If the control qubit is set to 1, target qubit is flipped. Basically, this is the equivalent is our XOR gate, right? If I know that one of the bit is 0, I can say they are okay. This is the equivalent one C naught gate. Like this, there are various gates in the quantum circuits, equivalent of classical computers. Okay. So this is the how we represent the quantum circuits. And the quantum programming also similar. You look like similar to that. Okay, quantum programming, quantum algorithms. What we talk about. This is a one quantum algorithm and we are representing that. Okay. So I'll just skip some of this one. So in classical circuits, we know the circuits very well know that number of input at every state I can measure it, I can predict it, I can predict. But whereas this is not possible. In quantum circuits looks like this. Okay. From any state of this state, I can go to the previous state. Right? Which is not possible, the irreversible part. And quantum algorithms, it's possible to solve problems. Right now, these are the ways people are looking at that, developing the quantum algorithms. We are talking about today quantum machine learning, quantum AI. These are one of the very talked about topics, and people can try for this one. Okay. People have demonstrated in the cryptography and biological, this one, some algorithms developed. Their circuits they are derived and all that. Okay. So Fourier transform we can do that. The complexity show that in a classical way, if you realize that how much complex it is, using the quantum logic, how much it is easier and all that, you can do that. How many operations and all that it is quite straightforward. And this is a normal design of the quantum bits, right? The quantum bit different type we can realize it. Hardware can be realized many ways. I told right 4 or 5 methods. The realization, it can be chemical, it can be physics. By physics is photons realized, chemical also they realize, electronic, the semiconductor methods also they realize and all. This is the cryogenic based quantum computers. Okay, D-wave and all that. Okay, there are various algorithms so far developed. Some of there are various algorithms you can have a look and all that. And there is already number of programming languages. And IBM has the QS is one of the programming languages. IBM QAC kit, Quantum Information Science kit. Like that, CDAC also developed one quantum computer, and they have their own. This one is realized right now. They are giving that operations free for the educational purpose. In the sense, you can go and work on those quantum computers. Okay, the quantum programs look like this. Okay. This is how the quantum programs look like. This is algorithm, logic, and all that. Okay, how it looks like in the QS language, programming language. Okay. So quantum computing architectures, the classical computer, and how we realize that there are various ways we can realize the quantum computers. Okay. Then few operations I'll say, implementation of quantum hydrogen, implementation method, that hardware realization, it can be liquid state, NMR, the Srinivas Rao, I was talking to you and all that, right? I was discussing about that. There are various ways we can realize this quantum particle qubits. These are the various methods, right? These are the various things which are available. I will share. So these are the various quantum computers, hardware candidates available. Uh, Various applications right now already, especially some of them. See, where are the linear equations? Okay, the weather applications are the linear equations. Flow applications are all linear applications. Like we use it in the aerospace and structural design and all that. We use the flow equations, right? So they are using that climatic modeling, financial analysis, cryptography, pharmacology, chemistry, travel logistics. Like the okay, you know the traveling salesman problem of 51 states. How complex it is? It is 10 states to traveling salesman problem in a computing this one algorithm is NP complete problem. You can, if you imagine 100 cities, it is a impossible. Like, that's why there is non-polynomial algorithms. So quantum factoring algorithms, people are already using that, and quantum search also they have demonstrated, and also the teleportation certain things are being demonstrated, but on limited quantum bits. This one, okay, and the quantum simulations people are doing that, and material design people are using the quantum computers right now. Okay, problem is the challenge is you have to develop your own algorithm, you have to develop your own circuit using the quantum computer to realize your functionality. That is a big challenge. These people can do that. Okay, they are using it in logistics, operational research, VLSI design, finance, and all that being tried. Okay, there are many applications. I'll skip that because okay, just for you to quantum teleportation explained and then it's already being demonstrated. Shor algorithm, we all know that. Computer people use the Shor algorithm, 64 bit and all that. And today 128 and 256 Shor algorithms are also being used. How different it is, computer science people are aware of that. Okay. So it is a quantum computing with IBM P6. Okay. Then this is a noisy intermediate scale quantum era. This is by different computer Caltech research groups working. NASQ. Okay, this various achievements they have done. Error migration, error correction. See, another quantum computing error correction is one of the state which is a challenge. Not that the number of bits realization is the problem, but at the state when you do the measurement, you have to do the error correction operations. That is, people are able to come out with algorithms for a few bits, not with the larger algorithms. Okay. Okay. Yeah, this is a race which is going on. 8,000 qubits, universal computer. People are walking out. Already this Google and other things announced that they bring the 2,000 qubit computer, Microsoft and all that. Okay, this is an emerging area. Gartner projects by today they are doing this much operation. 100 billions of this one in the next 10 years. Okay, with the applications and all. Okay. Yeah, the decoherence is a problem right now, error correction. These are some of the problems with the quantum computing. Okay, physical implementation is, there are many methods people understand. You have to write your own quantum algorithm for your application. Okay, these are the various books. A lot of literature is available, books are available. I can share some of the books which are. Okay.
Thank you, sir. Now I request everyone to join for a group photo. Please everyone assemble over the stage.